All right, welcome to a rare early morning video. I'm going to kick things off this morning with the reading that we were going to do for this. So this is the topic on IPv4 and IPv6 for routing policy, BGP routing policy. So I don't know what that beeping noise was that just happened, but we will continue on. So yeah, I've got 4 things I would like to read before moving on. I might have to cut some of them short just because I'm running low on time. I'm planning to take this in September, and that at this point leaves me probably around 110 days. One thing I did want to do though is start every video with just 5 correct answers from subnetting.net practice mode. I just want to get really comfortable with these numbers because they're going to be a huge part of the test. But I'm hoping that it'll come back to me really fast, so there won't be an issue. Yep, so I already got 2 right, so I just need 3 more. Right, so this one is kind of a difficult question. It's asking about so it's a class B. So the maximum number of valid subnets and usable hosts per subnet you can get from the network, 172.22.0.0. So I guess it's assuming that it's a class B address. But it is the class B private range, so I don't know if they mean throughout the just straight up class B or throughout the class B private range. But let's treat it as if it were just a straight up class B 255.255. So then we'd have 4 bits on. So the networks we get 4 bits to toggle. So that'd be 2, 4, 8, 16 subnets. And then the hosts per subnet, that would be the rest of those. So it would be 2 to the 12, which I'm just going to pull up a calculator for. Yeah, I think I'll have a calculator on the test. Yeah, so 4096. There's that beeping sound again. I'm really not sure what that's about. I've actually never heard that sound before. Okay, so I'm going to count that as a correct. I think this is 3, so I just got 2 more. So enter the subnet that the host belongs to. So it's a class B. So I think it's going to be so here's where yeah, oh, sorry, this is the not classfully speaking. So the class B range, this is going to fall under, it's going to fall under a private, which is not the /16, it's the /12, but they're asking for the network address. I just wasn't sure what they were asking for with the language they used, but this is a random host address within this subnet, so they want the network address. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8, and then 183. So you're going to have, this is how you get 180, and then you've got 3 there, and it's a /22. So a /20 is 4 bits in, 21, 22. So here's the marking. So these are going to be flipped to 0. So you're going to have 3 less, so it's going to be 180.0. All right, so let's do one more and then move on. What is the maximum number of valid subnets and usable hosts per subnet that you can get from that network? So, I mean, there's a lot of subnets because this is a Class A address. So it's going to be 2 to the 12 again, which is 4096 we know from before, and subnets, there's no special reservation for like a host subnet or a broadcast subnet. That's only for hosts. So host is going to be the same value, 20. It's going to be 12 bits, but here it's going to be 4094. There we go. So we got 5 right. Let's move on to do some reading now. So default routing policies. If an incoming or outgoing packet arrives and there is no explicitly configured policy related to the route or to the interface upon which the packet arrives, the action specified by the default policy is taken. A default policy is a rule or a set of rules that determine whether the route is placed in or advertised from the routing table, or whether the packet is accepted into or transmitted from the router interface. You must be familiar with the default routing policies to know when you need to modify them to suit your needs. Table 1 summarizes the default routing policies for each routing protocol that imports and exports routes. The actions in the default routing policies are taken if you have not explicitly configured a routing policy. This table also shows direct and explicitly configured routes, which for the purposes of this table are considered a pseudo protocol. Explicitly configured routes include aggregate, generated, and static routes. Importing or exporting protocol, default import policy, default export policy. So for BGP, the default import policy is to accept all BGP IPv4 routes learned from configured neighbors and import into the inet.0 routing table. For IPv6, it is to accept all received BGP IPv6 routes learned from configured neighbors and import into the inet 6.0 routing table. The default export policy for BGP is to re-advertise all active BGP routes to all BGP speakers while following protocol-specific rules that prohibit one iBGP speaker from re-advertising routes learned from another iBGP speaker unless it is functioning as a route reflector. All right, so default import policy for DVMRP, accept all DVMRP routes and import into the inet.1 routing table, accept and export active DVMRP routes. For ISIS, it is to accept all ISIS routes and import into the inet.0 and inet.6 routing tables. For the import, for the export, reject everything. This protocol uses flooding to announce routes and any learned routes. Okay. LDP, accept all LDP routes and import into the inet.3 routing table. On export, reject everything. MPLS, accept all MPLS routes and import into inet.3 routing table. Export, accept, and export active MPLS routes. OSPF, accept all OSPF routes and import into the inet.0 routing table. You cannot override or change this default policy. On export, reject everything. The protocol uses flooding to announce local routes and any learned routes. All right, so for PIM dense mode, accept all PIM dense mode routes and import into the inet.1 routing table. Accept active PIM dense mode routes. PIM sparse mode, accept all PIM sparse routes and import into the inet.1 routing table. For export, accept and export PIM sparse mode routes. And for pseudo protocol, such as direct routes, explicitly configured routes, such as aggregate routes, generated routes, or static routes. On import, accept all direct and explicitly configured routes and import into the INET.0 routing table. On export, the pseudo protocol cannot export any routes from the routing table because it is not a routing protocol. Routing protocols can export these or any routes from the routing table. Okay, so first thing that came to mind is like, what the heck, this makes no sense, because we showed very clearly that we have static routes being exported out. Like, that's how we did all of our testing for those last BGP examples. Well, you can't export a static route through the static routing protocol. It's not even really a routing protocol, it's a pseudo protocol. So when you go into your routing table and you see it's static, or you see it's direct, or even aggregate or generated, those aren't real routing protocols, and you cannot use them to export a route. What we did in the exercise is we exported them into a real routing protocol. In our case, we used BGP. So for RIP, imports, accept all RIP routes learned from configured neighbors and import into the INET.0 routing table. On export, reject everything. To export RIP routes, you must configure an export policy for RIP. For RIP-NG, which is the IPv6 version of RIP, on import, accept all RIP-NG routes learned from configured neighbors and import into the INET 6.0 routing table. For export, reject everything. To export RIP-NG routes, you must configure an export policy for RIP-NG. Test policy, accept all routes. Yeah, and then we can configure a testing policy with complex regular expressions. So it looks like this is all, yeah, specific to, yeah, VRFs and layer 3 VPNs and ISIS and OSPF. So nothing that's going to be on the test, and even most of what I read there, sorry, it's going to be on the test, but nothing that's going to be on the test for this topic. So let's see if I can find, aha, here it is. So I'll get to cross this off. So let's move on to the next one. Yeah, and they keep popping up, so I definitely don't want to just keep getting behind. So let's just keep it moving. The walk-up feature, I don't know if I want to read about that. I do want to read the route filter examples. So the examples in this section show only fragments of routing policies. Normally, you'll combine these fragments with other terms or routing policies. In all examples, remember that the following actions apply to non-matching routes. Evaluate next term if present. Evaluate next policy if present. Take the accept or reject action specified by the default policy. For more information about the default routing policies, and we just read that. So let's see if there's any specific example I want to learn more about. If there's anything in IPv6, I think that's obvious that I definitely want to look at that. But yeah, I don't think I need to read through this. I don't see anything specific to IPv6 too. So I'm gonna kind of make up some time and skip that. Of course, that's probably exactly what's going to be on the test, but that's okay. All right, but let's look at walkup. So use the walkup feature if you have concerns about policy performance because of split route filters across multiple policy terms. The walkup feature enables the consolidation of route filters under one policy term. By default, Junos evaluates multiple route filters in a policy statement term by first finding the longest match prefix and then evaluating the conditions attached to the route filter, such as prefix range. If the route filter condition is false, for example, the prefix is not in the specified range, then the whole term is false, even if there are potentially true shorter route prefixes. Due to this behavior, there can be performance issues if route filters are split into individual policy statement terms. The walkup feature changes the default route filter behavior. Some automated policy tools, for example, those used for autonomous system border routers. I think I found what's beeping, and I'm turning it off. Break up route filters into multiple terms because of the default route filter behavior. Route filters are also used in routing protocols other than BGP. The walkup feature is not limited to BGP route filters. Technically, BGP does not deal with routes in the same way as OSPF or ISIS. BGP routes are more properly called network layer reachability information, LLRI updates. However, the term route is used in most documentation and is used here. That's an important distinction to make, because with OSPF and ISIS, you get those actual routes, and you get the whole route, and it's called a route, and everything is good and makes sense. But in BGP, you get what's called a prefix. You don't even get technically a route. And not only that, you get a whole bunch of other stuff with the route. You get the AS path, you get the origin, and you get the next hop. So you get those well-known mandatory attributes with every single one. So, and then it's called a prefix. So it really is something else. It's a network layer reachability information update, and it's not a actual route. BGP protocol uses that information to put a route in the table, but that information is not the route itself, unlike other protocols. Route filters consist of three major parts: a prefix and prefix length, for example, that's a match condition, for example, exact, an action that is carried out if both previous parts, the prefix and match condition, both evaluate to true, for example, accept. So there succeeds, okay. Route filters can be combined in a single policy term. Note that, okay. By default, there's perfect. Yeah, that's good based on the results. Yeah, I'm going to read the rest of this. So based on the results of these first, okay, note that or longer includes the prefix there and there. In range by default, the evaluation of a policy statement term with multiple routes is a two-step process. The policy framework software performs a longest match lookup on the list based on prefix and prefix length values. The software considers the route filter condition or longer exact and so on. The route either fulfills the route filter condition success or does not match the route filter condition failure. Based on the results of these two steps, the action determined by the match or failure is applied to the route. In route filter -A, this means that any route that is true is accepted, and any route that is false in route filter -A term is rejected. This route becomes a hidden or filtered route. For example, consider what happens when a route 10.0.0/18 is evaluated by the policy statement route filter A, which we have up here. So this is that, what is it, -19 or -18. So prefix length range. So it'll definitely match this one, but it will also match this one. But this will be the most specific match because it only goes up to that range. Yeah. First, the 10/18 route is evaluated by the route filter 1 term because 10/16 is longer than 10/8. The 10/18 route matches the longer and more specific prefix. Okay, yep, so I got that right. So it's going to be accepted, but okay. Next, the match fails because the 10/18 route does not match the prefix length range 10/22 through /24 conditions. So the route match fails in the route filter 1 term, and the policy examines the next term, the default term. The 10/18 route is rejected by the default term. Okay, so it essentially is a two-step process. It first evaluates this part, and then it evaluates that part. So on this part, /18 is a longer match, so it's going to go with this, but the prefix length range has to be between 22 and 24, which 18 does not fall into. So even though it would have been all good if it matched here, this was the longer match, but it had extra qualifiers here that it did not match. So it's going to get rejected by this statement, even though if you didn't have this statement on here, it would have been fine here. Or if you, yeah, even though it does match here, and since this is the longest match, and it has extra qualifiers that 10/18 does not fall into, it will be rejected. So the route match fails. Yep, it's rejected by the default term. As a result, 10/18 route is hidden, filtered. The 10/18 route can still be fine with the show route hidden command. The issue is that the user might actually want the 10/18 route to be accepted, not rejected. Naturally, a route filter with 10/18 exact configuration could be added. Yeah, like what's wrong with that? Like that, exactly. So you can just go here. So yeah, 16 is the longest match, but I add a new one, 10/18 exact. I've got that exact route. That's perfect. So what's wrong with that? But in a backbone routing table with 100,000 or more entries, and I will say in my experience, or more can mean quite a bit more than 100,000, at least half 100,000. One thing you can do, and let's do this here. Let's go to a BGP looking glass server, and there's companies like AT&T, NTT, Cogent, that will let you look inside of their BGP servers for free. I mean, it sometimes helps. It helps other providers to know. Like, and for example, let's say, oops, there's my public IP. I kind of don't want to show that. Well, hopefully it's there enough. Oh, okay, yeah, there we go. So let's do a test. We're gonna do BGP. Yeah, Frankfurt. Oh, and I would have to enter in my like address and shit, which should just popped up there too, which is a bad thing. I don't want to show that, but yeah. So this is kind of not good. But that's something we could do if I weren't concerned about broadcasting all of my public information through YouTube. All right. So naturally, a route filter could be added, but in a backbone routing table with that, it's not possible. Yeah. But in backbone routing, yeah, it's not possible to configure a route filter tuned to every possible route and every possible new route added to the network, of course. The default workaround to achieve proper behavior from the example routing policy is to configure a separate term for each route filter. This is generally done as follows. Okay, so now It's going to evaluate the terms sequentially, and it won't pass this term because, yeah, it matches, but it doesn't match in there. So now we'll go to this next term, and it will be accepted from there. Now the 10/18 route is accepted because although it still fails the route filter 1 match condition, it matches the new route filter 2 term. 10/8 is the longest match, and the or longer condition is true. So you've got a match, and then you've got qualifiers or conditions. The problem with this approach is that the complete routing policy now takes more time to evaluate than when multiple route filters are grouped. This method also makes maintenance more complex. The issues with the one term per route filters approach are solved with the walkup statement and feature. Walkup alters the default behavior of route filter evaluation globally or on a per policy basis. The walkup feature allows terms with multiple route filters to walk up the evaluation process to include less specific routes as well as the longest match. In other words, the walkup knob changes the default behavior from if one fails, then the term fails, to if one matches, then the term matches. Consider the application of the walkup feature to the example policy statements. You can also apply walkup globally to all policies configured. So route filter, okay, so this is defaults. Let's actually try to put this in one of the devices, because this, I have a feeling, because I guarantee you on the test, I'm just going to be hit with the most stress-inducing list of route filter statements that I could possibly be hit with. So if it's just a matter of enabling this knob walkup and then not having to split those into multiple terms and just having it take the ones where it match, take actions based upon the ones where it does match, instead of taking actions based upon the longest match and then doing the qualifiers, I can save myself a lot of time and energy. So this walkup knob, I think, is going to be important to know about. So let me try to put it into the policy. Oops. So edit routing. Oh, sorry. Edit policy options. Perfect. Policy statement. We're going to call it test walkup knob. So now let's see what we've got. So we've got, so policy default behavior. So let's go into that and see if there's more stuff besides just walkup that might be good to learn about. So I don't see walkup anywhere. Let's see here. So, oh, no, it's under route filter. So route filter, set route filter behavior. So there we go, walkup. So if I have this situation on the test where I've got route filters just out of control and I want to route through, I might be able to save myself hours of troubleshooting and splitting that into multiple terms by just enabling that walkup feature. And then really all you're graded on is whether or not you can actually reach the routes and have the pings work as they want you to. You're not graded on the method you use to get there. So I can save myself hours in that section of the exam just by enabling route filter walkup. This is what happens when the route prefix 10/18 is evaluated by the statement route filter -a. The default behavior is altered by the walkup knob. As before, the 10/18 route matches the longer and more specific route prefix because 10/16 is longer than 10/8. As before, this match fails because the 10/18 route does not match the prefix length range. /22 through /24 condition. However, this time the process continues by walk up and examines the less specific 10/8 route filter. I got to admit, like when they say like, you know, this time it uses a walk up, you know, it's so clear that it's using a walk up. That's not how I would consider the term walk up to be used. Like, I think a better word would be, let me just finish reading this section. The route condition of or longer matches this filter, and therefore the route is accepted by the route filter -1 term. This can be verified for a BGP route by the show route protocol 10/18 command. This time the route is not hidden. If you enable the walkup feature globally, you can override it locally on a per policy basis. Aha, so this is kind of nice, because I was wondering, you know, why do you have the option for no walkup, because you just don't have to enable walkup. But what you can do is just set the knob walkup as I have here. So show pipe display set. You can see I've got under policy options. So instead of putting it in its own policy statement, I can just say edit policy options, defaults, route filter, and then set walkup. And now on any policy where I don't want that walkup, any policy statement, so let's say I want it on change local preference, but I don't want it on send direct term. Now I can just go in here and do defaults, route filter, no walkup. So that's the value of that no walkup statement, which I think can be really valuable. So now let's think for a minute or two what I would name it, because walkup, in my opinion, really isn't a good name for it. Now, if the conditions were matched such that, so let's say that these here are conditions, and if the default way to evaluate them would be top to bottom, and the walkup feature changed it to so that they were evaluated bottom to top, then yeah, that would make sense for me, walk up instead of walk down. But clearly that's not what it does. What it says is, so you're going to have it match here. So I'm going to send you a number 1 through 4. I send you 2. So it matches here, but I'm going to send you a statement after that. I'm going to send you more information, and whether or not it's accepted is based on that information. So even though there was another 2 there, let's say I send you 21, and it just looks, and the longest match I've got is 2, so I have 2 in there twice. But the look before you leave statement disqualifies what I sent you from going through. Without walkup on there, that's what it will do. It will not go and look at one that is a less specific match. So let me read again. So in other words, the walkup knob changes the default behavior from if 1 fails, then the term fails, to if 1 matches, then the term matches. So that's yeah. So here I think was a really good example. So /18, the longest match is going to be here, but it's not going to be qualified there. So this one doesn't match. Now this one does match, but without walkup enabled, this one already failed. So at that point, you go down to the next term. Now, if you have walkup available, walkup turned on, okay, yes, still same thing. This match, this is the longest match, but it was rejected. But now we've got walkup on, and it matches this, so it's going to go with that because it matches. So a better term than walkup, I would think, would be like until match, or matching always, or last resort would even be good, or match until last resort. But yeah, walkup, kind of, I don't really understand where that language, like what the thinking behind that statement is. Something more like match until found. That would be a good one too. I mean, it's a little bit wordy, longer than walkup, but I think I've offered a few that I think would be better than walkup, or at least be more clear. But yeah, I mean, walkup is a concise term. It's I don't think hard to remember, and yeah, it could save me hours on the exam where I would have to rewrite those policies to be in separate terms. I can just use walkup and move on with the next topic. All right, so we're coming on 7:28 right now, and it looks like we've only got one left to read. So we've already read, I think, this part. Oh no, we haven't read. No, we definitely haven't read any of this. But well, yeah, we've read the examples, but we haven't read anything. Oh, we did read that. Yeah, we've read here. So let's just read this part up here. So understanding route filters for use in route match policy. Yeah, and this is to say, don't read this until you've configured. We have read this part. So radix trees. To understand the operation of a route filter, you need to be familiar with a device used for binary number matching, known as a radix tree, sometimes called a Patricia tray or radix tray. A radix tree uses binary lookups to identify identify IP addresses or routes. Remember that an IP address is a 32-bit number represented in a dotted decimal format for easy comprehension by humans. These 8-bit groupings can each have a value between 8 and 255. A radix tree can be a graphical representation of these binary numbers. In Figure 1, the radix tree starts with no configured value, starts at 0, and is at the leftmost position of the binary IP address. This is shown as 0/0, which is often referred to as the default route. Beginning of a radix tree, 0/0, and then here's the good old-fashioned 128, 64, 32, 16, 8, 4, 2, 1 essential values to have committed to memory. Because this is binary, each bit can have only one of two possible values, a 0 or a 1. Moving down the left branch represents a value of 0, while moving to the right represents a value of 1. The first step is shown in Figure 2. At the first position, the first octet of the IP address has a value of all zeros, or the first one is a 1 and then the rest zeros, or a 0 or 128 respectively. This is represented in Figure 2 by the values 0/1 and 128/1. The next step is shown in Figure 3. The second level of the tree has 4 possible binary values for the first octet. These decimal values of 0, 64, 128, and 192 are represented by the IP addresses of 0/2, 64/2, 128/2, and 192/2 on the radix tree. All right, so the step-by-step process continues for 33 total levels to represent every possible IP address. The radix tree structure is helpful when locating a group of values that all share the same most significant bits. Figure 4 shows the point in the radix tree that represents the 192.168.0.0/16 network. All of the routes that are more specific than 192.168.0.0/16 are shown in the highlighted section. So let's see here. So this is the full radix tree with the 33 levels. Level 0 here, level 33 down there. So here's this part. So these are all the more specific matches. Configuring route filters. The topic configuring route filters describes default Junos OS behavior, the walkup feature, which is not discovered, discussed, not covered in this topic, alters the evaluation results discussed in this topic by allowing the router to consider shorter match conditions configured within the same term. It's kind of funny. I actually like this explanation of it better than anything that was written here. They gave a more clear, more concise explanation of what this whole document was saying in one sentence in a related document. So to configure a route filter, include one or more route-filter or route-filter-address statements. The route filter option is typically used to match an incoming route address to destination match prefixes of any type except for unicast source addresses. The destination prefix address is the IPv4 or IPv6 address prefix specified as prefix/prefix length. If you omit prefix length for an IPv4 prefix, the default is /32. If you omit prefix-length for an IPv6 prefix, the default is /128. Prefixes specified in a from statement must be either all IPv4 addresses or all IPv6 addresses. The source address filter option is typically used to match an incoming route address to unicast source addresses in multi-protocol BGP, MPBGP, and multicast source discovery protocol, MSDP environments. Source prefix address is the IPv4 or IPv6 address prefix specified as prefix/prefix length. If you omit prefix-length for an IPv4 prefix, the default is /32 prefix length. If you omit prefix-length for a IPv6 prefix, the default is /128. Prefixes specified in a from statement must be either all IPv4 addresses or all IPv6 addresses. Match type is the type of match to apply to the source or destination prefix. It can be one of the match types listed in Table 1. For examples of match types and the results when presented with various routes, see Table 2. Actions are the actions to take if a route address matches the criteria specified for a destination match prefix, specified as part of a route filter option, or for a source match prefix specified as part of a destination address filter option. The actions can consist of one or more actions described in actions in routing policy terms. In a route filter, you can specify actions in two ways: the route filter or route source address filter option. These actions are taken immediately after a match occurs, and the then statement is not evaluated. In the then statement, these actions are taken after a match occurs, but no actions are specified for a route filter or source address filter option. The up to and prefix length range match types are similar in that both specify the most significant bits and provide a range of prefix lengths that can match. The difference is that up to allows you to specify an upper limit only for the prefix length range, whereas prefix length range allows you to specify both lower and upper limits. So, I mean, these are all self-explanatory, long drawn out explanations for things that are self-explanatory. I don't think the radix tree really is a super useful concept. I'll just keep this in mind, and I'll come back to it if I have trouble with understanding what matches, but I really don't think I'm having trouble with that right now. So I'm going to keep that in mind. Radix trees, Juniper radix trees. I'm sure I can get back to that really fast. Yeah. So if I just type in Juniper radix tree, which I know is associated with routing policy and specifically using a route filter to match conditions within a routing policy, I can come back and I can brush up on this if I'm ever lost and can't figure out why something is working the way it does. I don't know if I can do that during the test, but I will keep that in mind. So, all right, I'm going to rename this to done. So this was a shorter one, hopefully. Next one is going to be a lot more exciting, a lot less just straight up reading. This is going to be a really good lab associated with this one. It's learning about the multipath knob in BGP and how that can be used for load balancing BGP traffic. So we're going to have, let's see here, 1, 2. So we're going to have 2 really solid examples to go over in the lab and learn all about BGP load balancing. So stay tuned. Hope you enjoyed this topic and enjoy the rest of the day. See you at lunch.